Session 1 of the chapter, ray optics. Optics is a branch of physics that deals with study of light. Light is a form of energy that makes the things visible. Light is an electromagnetic wave. We know that the electromagnetic waves range from gamma rays to radio waves, like gamma rays, X-rays, ultraviolet rays, VIB-Guyot, infrared rays, microwaves and radio waves. Among these electromagnetic waves, only VIB-Guyot region is visible to our eyes. That is why this region is called as visible light or simply light. And the wavelength of this visible region ranges from 4000 Armstrong to 8000 Armstrong. And the electromagnetic waves which lie between 4000 Armstrong to 8000 Armstrong wavelength, that electromagnetic wave is called as visible light or simply light. From dual nature of radiation and matter, we came to know that light has dual nature. Sometimes light behaves like a particle, and in others sometimes light behaves like a wave. The next question arises here is, when does the light behaves like a particle and when does the light behaves like a wave? And it depends upon the dimensions of the object on which light falls. The behavior of the light depends upon the dimension of the object on which the light falls. Based upon this duality, optics can also be divided into two types. One is ray optics and another one is wave optics. Ray optics is also called geometrical optics. Wave optics is also called as physical optics. Now, let us understand what we will be studying under ray optics. Here, we study about the objects whose dimension is very large compared to the wavelength of light. So, what is wavelength of light? From 4000 Armstrong to 8000 Armstrong, right? So, if you are taking an object whose dimension is very large compared to the wavelength of light, and if we study the interaction of light with this matter, that session we will be studying under the section ray optics. Means here we will be studying the interaction of light with the lens, mirror, prism and any other object whose dimension is very large compared to the wavelength of light. Then the light behaves like a particle, right? So if a particle falls on an object, it comes back. In the similar manner, if a light falls on the object, it also comes back. So that phenomena is called as reflection of light, right? In day-to-day life, we will be seeing the things whose dimensions are very large compared to the wavelength of light. So in most of the time, we will be finding this section, right? We will be finding the properties which are related to the ray optics. There is another one optics called as wave optics. So in this section, we will be studying the interaction of light with an object which is very small, whose dimension is nearly equal to the wavelength of light, means from 4000 Armstrong to 8000 Armstrong, nearly equal to these wavelengths. If I am taking the dimension, then there we can find behavior of the light in the form of waves. So those things we will be studying under the wave optics, right? Here the dimensions of the objects are very near to the wavelength of light. Now let us begin with ray optics. Ray optics is the study of propagation of light in terms of rays. Means here we will be seeing the objects whose dimensions are very large compared to the wavelength of light. If we study the propagation of light in terms of rays, it is called as ray optics. If we study the propagation of light in terms of waves, it is called as wave optics. Okay, this session will be on ray optics. Then, what is the meaning of ray? A ray is a path traveled by light. Okay, if the light is moving in this direction, we can represent it by a ray, right? And the arrow mark represents the direction of light. The path traveled by light is called as a ray. In this chapter, I will be using the word called a beam of light. Means beam is nothing but the bundle of rays. If there is a source, it emits light. And the rays will be in the form of bundles. And that time, I will be calling it as beam of light. So beam is nothing but the bundle of rays. And one of the important property of light is rectilineum. rectilinear property of light. So what is the meaning of rectilinear property? That is, the light travels in a straight line. Always light travels in a straight line in a medium. For example, this is a medium, light always travels in a straight line, and the shadow is the example for the rectilinear property of light, right? So as the light travels in a straight line, so I can see the shadow exactly at that position, right? Means the size of the shadow depends upon the position of the sun here, right? So that is one of the proof for a rectilinear propagation of light. Now let us understand what is the speed of light. The speed of light depends upon the medium in which it travels. The speed of light in vacuum is equal to 3 into 10 raised to 8 meter per second, and it is represented by small letter c. Means the speed of light is 3 lakh kilometer per second. Do you understand how much speed the light is, right? In 1 second, light travels 3 lakh kilometer. So that is the speed of light. It is the fastest thing in nature. That is about the light. Light travels with the speed of 3 into 10 raised to 8 meter per second. And the medium in which the light travels, that medium is called as optical medium. It is a medium through which light propagates, right? So certain medium are there in which light propagates, like air, it is an optical medium, water is an optical medium, glass is an optical medium, right? So the medium through which light travels, that medium is called as optical medium, and the medium through which light cannot travel, that is called as opaque medium. For example, if I am taking a wood, if I take a metal plate through which the light cannot travel, so that kind of medium are called as opaque medium, right? The medium through which the light propagates, that medium is called as optical medium. Let us see the applications of reflection of light. At our home, the mirror what we use, that is plane mirror. It produces the image of the same size and at the same distance from the mirror. There we have a silvered surface, or we call it as a reflecting surface at the front, and which is non-reflecting surface or wooden surface at the back. So that kind of mirror is called as plane mirror, where the reflecting surface or the silvered surface is flat. So that kind of mirror is called plane mirrors. But there are some mirrors which are curved, and those mirrors are called as spherical mirrors, and they have lot of applications in our day-to-day life. They are called spherical mirrors because these mirrors are the part of a sphere. Let me take a spherical reflecting surface. There is a sphere and there is a reflecting surface. For example, let me take this is a sphere and the reflecting surface is inside, okay? The silvered surface where you can see your face, that is inside. Now here, let me take in that way here, and this is a spherical reflecting surface, and if I cut this spherical reflecting surface, I will be getting a spherical mirror. So what is a spherical mirror? Spherical mirror is a part of spherical reflecting surface. There is a spherical reflecting surface and it is a part of that. That is the name, that is why the name spherical mirrors. And these spherical mirrors are of two types based upon where actually the reflecting surface is. Is reflecting surface inside the curve or reflecting surface outside the curve? Based upon that, we will be dividing spherical mirrors into two types. One is concave mirror and another one is convex mirror. Okay, the same mirror I will be taking here. But in the first case, let me take the reflecting surface is inside the curve, and you can see your face inside now here, right? Inside the curve. So if the reflecting surface is inside the curve, then that kind of mirror is called as concave mirror, right? You can remember like this, cave is something which is inside. If reflecting surface is inside the curve, then that kind of mirror is called as concave mirror, right? So in the second part of the mirror, that is convex mirror now here. There the reflecting surface is outside the curve. For example, you cannot see your face this side now here, but you can see your face this side. If the reflecting surface is outside the curve, then that kind of spherical mirror is called convex mirror. Okay, we have started with spherical mirror. Spherical mirror is a part of spherical reflecting surface. There are two types based upon where actually the reflecting surface is. If reflecting surface is inside the curve, then it is called as concave mirror. If the reflecting surface is outside the curve, we call it as convex mirrors. Now, let us check it out how actually the image is formed in these kind of mirrors. Let us begin with the first one, that is concave mirror. Okay, let me take a spherical mirror like this. So this is a spherical mirror and the reflecting surface is inside. So let me take like this. So it represents that the silvered surface or the reflecting surface is inside the curve. Now let me check it out what actually happens if the light falls on this mirror now here, right? If the light falls like this, this is a ray of light. Let me consider it falls on the mirror. Then what happens? This ray of light which falls on the mirror at exactly at the center, it reflects back in the same path. Why it reflects? Let me tell you. Before, let me explain another one ray, then I will be coming back to this ray now here. Okay, let me consider here. If I am taking a ray in this path now here, okay, it hits the surface. Now again, since this ray reflects, let me use law of reflection. What is the law of reflection? Angle of incidence must be equal to angle of reflection. Okay, let me consider then where is the normal here. Okay, to calculate normal, you know, it is a normal is a perpendicular line drawn at the surface. Okay, let me consider like this. So as we know, spherical mirror is a part of a spherical reflecting surface. The ray exactly falls at this position now here, right? And this is the center of the sphere and we are not having these all things now here, right? Now, what is the perpendicular line to that point of incidence now? Okay, if I am drawing a tangent here, if I am drawing a tangent and you know the radius is the perpendicular, this line is perpendicular to the tangent. So this line becomes normal. Then what is this angle now here? This is angle of incidence. Then where is reflected ray? Reflected ray must be in this place itself because the normal is here. From the normal, the angle of reflection must be equal to angle of incidence. So if it is angle of incidence, the reflected ray must come back like this and it makes an angle which is equal to the angle of incidence. This is how if the ray of light hits the mirror, it comes back at this position because it obeys law of reflection. Okay, now let me check it out. Okay, this is a part of spherical reflecting surface now here. Okay, now when it comes here, there is a normal and if I'm taking, it comes back like this. So this is reflected ray and this is incident ray. Okay, now let me ask you one question here. What happens to this ray? This is a ray which hits exactly at the center of the mirror. Okay, now let me check it out again. This is a part of spherical reflecting surface and we know there is a sphere like this, right? It is a sphere. If this is the angle of incidence like this, now come on, tell me where is the normal now here? Okay, let me take a tangent here. If I'm taking a tangent, where is the perpendicular line to that tangent? Okay, this line itself means the normal lies on the incident ray itself. Then what is the angle of incidence? 0 degree. If angle of incidence is 0 degree, then what is angle of reflection? It must be 0 degree. That is the reason why the ray traces back in the same path when it hits at the center of the mirror. Right? So this is the reason why the ray of light traces back when it hits at the center of the mirror. Okay, let me take like this now here. There is another one ray, this is called as incident ray and it hits at the concave mirror. Right? When it hits, again, where is the normal here? This is the normal. Where is the reflected ray? It must, the reflected ray must pass in this way itself. When it hits the mirror, it must pass in this way. Right? So like this, concave mirror converges the parallel rays which falls on it. That is the reason why concave mirror is called as converging mirror. Right? So this mirror is called as converging mirror because this mirror converges the parallel rays of light which falls on the mirror. Right? In the similar manner, let us draw the rays of light to convex mirror. Okay, let me consider. Okay, this is a convex mirror. I already told you, convex mirror is a mirror whose reflecting surface is outside the curve. Means you can see your face outside the curve here. That is, the silvered surface is outside the curve. Okay, let me check it out. What happens now here, right? So this is a ray which falls exactly at the center of the mirror, and you know that when it falls, it retraces its path because normal is on the line itself. Now let me check it out. What will happen if this ray falls on the convex mirror? Okay, if I am taking, this is an incident ray. Now let us check it out, where actually the reflected ray must go. Will it come this side or will it come that side? It depends upon where actually the normal is, right? Okay, how to draw the normal? Okay, I already told you, draw a tangent here. If I am drawing a tangent, draw a perpendicular line. Okay, where is a perpendicular line? We know this spherical surface is part of a spherical surface now here. Where is the center? This is the center. Then where actually the normal is? Normal is like this. If I am drawing, this is the normal. Then where is the angle of incidence? This is the angle of incidence. Then where must be angle of reflection? Of course, angle of reflection must be this side now here. That is the reason why reflected ray will reflect in that direction here. Okay, the reflected ray must be like this, right, in that way. So what is this now here? This is the angle of reflection, and it must obey the law of reflection. Angle of incidence must be equal to angle of incidence must be equal to angle of reflection. That is the reason why convex mirror diverges the ray, concave mirror converges the ray, right? This is the reason here. Okay, let me check it out now here. Okay, let me take like this. If a ray of light falls on the mirror, it diverges in this way now here, right? And again, if I take the same ray here, and again there will be a normal, and the reflected ray will be like this, and it appears to come from a point now here, right? So these rays are diverged when it falls on the mirror. That is why the convex mirror is called diverging mirror, right? Let me call the convex mirror is called as diverging mirror because it diverges the parallel rays of light which falls on that mirror, right? So concave mirror is converging mirror, convex mirror is diverging mirror. Okay, where we will be using this kind of mirrors in day-to-day life? Concave mirror. When we see the concave mirror, it enlarges the size of the object now here, right? That is the reason why concave mirrors are used in shaving mirrors, right? So in shaving mirrors, it needs to enlarge the object. Because of this reason, in shaving mirrors, concave mirror is used now here, right? So convex mirror, we know that convex mirror is used in driver's mirror. Okay, there is a driver's mirror which is convex now here, right? So it can see the large object which is behind now here, right? So convex mirror is used in a driver's mirror, and a concave mirror is used in shaving mirrors. So these are some of the spherical mirrors which have application in day-to-day life. Now let us see what are the terminologies what we use for spherical mirrors. Okay, these are two spherical mirrors. Here the reflecting surface is inside the curve. Inside means it is cave, that is concave mirror. Here reflecting surface is outside the curve, then it is called as convex mirror. One thing do understand, these mirrors are the part of spherical reflecting surface. And what are the terminologies what we use? Okay, let us move on the first one, that is pole. Where is the pole of the mirror? Pole of the mirror is the midpoint of spherical mirrors. For example, if this is a concave mirror, this is the midpoint and this point is called as pole. And for convex mirror, again, this is the midpoint of the mirror and we call it as a pole here, right? Pole is the midpoint of spherical mirrors. So this is the first terminology. Second, what is the center of curvature? We will be using this kind of words. What is the center of curvature of a spherical mirror? Center of curvature, the name itself says center of curvature is the center of sphere of which mirror is a part. For example, if this is a mirror here, right, if we extend that, I will be getting a sphere now here, and the center of the sphere is nothing but the center of curvature. Let me take like this. And here also, if I complete that, the center of the sphere is called as the center of curvature now here, right? So center of curvature is the center of sphere of which mirror is the part. For example, this is the mirror. Let me consider this is the reflecting surface and this is a concave mirror. Where is the center of curvature? I need to imagine a sphere here. If I imagine a sphere, here I will be getting the center of the sphere, and this center is called as center of curvature. Now, let us move to the third terminology, that is a radius of curvature. What is radius of curvature? Again, it is a radius. It is the radius of sphere of which mirror is a part. For example, so what is the radius of sphere? So this is the radius of sphere, and this radius of sphere, this radius of the sphere is called as radius of curvature. Here, where is the radius of curvature? Okay, this distance. The radius of the sphere itself is the radius of curvature. So what is the radius of curvature? It is the radius of sphere of which mirror is a part. Now let us move to the next one, that is principal axis, that is the main axis. What is principal axis? It is the line joining pole and the center of curvature. Where is pole? This is pole, and this is center of curvature. If I am drawing a line which passes through center of curvature and pole, and this line is called as principal axis. The line joining the pole and the center of curvature, right? So this line is called as the principal axis, right? Now the next terminology what we will be using here is principal focus. The name itself says focus means something is focusing at that point now here, right? What is principal focus? And we denote it by capital letter F. Principal focus is the point on principal axis. Do you understand? It is a point on principal axis where the rays of light parallel to principal axis meet. Okay, we have already seen in the last session that if I am taking a parallel rays here, it will meet at a point. And the point at which these rays meet, for example, if I am taking here, that point is called as principal focus. In concave mirror, these parallel lines meet, but in convex mirror, the parallel line will not meet, they will diverge, but they appear to meet at a certain point. So this point is called as the principal focus. So considering both the mirrors, I will be stating like this: point on principal axis where the rays of light parallel to principal axis meet, that is in case of concave mirror, or appears to meet, that is in case of convex mirror, that too after reflection, and that point on the principal axis, that point is called as principal focus. Now the other one thing, the next terminology what I will be using is about focal length. What is focal length? It is the distance between pole and the principal focus. Okay, where is that now here? Here. This is a pole and this is the principal focus, and this distance is called as focal length of the mirror. Okay, where is focal length here? This is right. So the distance between pole and the principal focus is called as focal lengths. Right. So these all are the terminologies that we will be using for the spherical mirror. Right. Let us move on to the sign conventions used for the distances measured from mirrors. That we will be studying under Cartesian sign convention. Okay, let us move to the first one, that is all the distances are measured from pole. Okay, this is the rule that you need to remember, that whatever we measure the distance from the mirror, it should be measured from the pole itself. Okay, let us take both the mirrors and understand what are the sign conventions here. Okay, let me take first concave mirror. Okay, this is the concave mirror. Okay, concave mirror is a mirror whose reflecting surface is inside the curve. That is the concave mirror. Okay, next let us move to the convex mirror. Okay, this is a convex mirror whose reflecting surface is outside the curve. Okay, this is the reflecting surface and this is not. Let me take like this. And we have already studied that. Where is pole in this mirror? Pole is the midpoint of the mirror. Okay, let me take, where is the midpoint? This is the midpoint, and let me call it as pole. And where is the midpoint in convex now here? So this is the midpoint, let me call it as pole now here. Okay, which mirror this is? Let me call it is a concave mirror. And what is this? This is a convex mirror. Okay, now for these two mirrors, let me draw principal axis, that is main axis. Always the principal axis will pass through the pole. Okay, here where is the principal axis? Okay, this is the principal axis, it passes through the pole. Okay, what is the first sign convention? All the distances are measured from pole. Okay, whatever distance you measure in mirrors here, it should be measured from the pole itself, right? For example, if I take object here, if I am taking object here, right, what is the distance of object from the mirror? Okay, where I need to measure here? I need to measure it from the pole. Okay, I need to take from pole and I need to measure the distance, right? Everything, whatever measurement you do, you need to take it from the pole. Why we need to take it from the pole? Okay, that is the rule here, right? So by taking that, we can assign the signs. Either the distance is positive or negative. It depends, right? So let me take the distances are always measured from the pole. Okay, now, so this is the rule here, right? This is, let me take like this now here. And if I'm taking an object here, okay, this is the object if I'm taking. Okay, object distance is always measured as u here, right? So u is a letter which is used for object distance. Okay, whereas this is the object distance, that is u. Let me call this is the object distance, right? And we know that the distances are measured from the pole. Okay, from the pole I will be measuring the distance, that is u here, right? Okay, now the second sign convention says that distance measured in the direction of incident ray is taken positive. Okay, first you need to understand where is the direction of incident ray here. Okay, if object is here, right, for example, let me take like this, there is no confusion like this. If the object is here, let me take this is the object now here, right? If the object is here, where is the incident ray? It always, the incident ray is like this, always the ray comes from the object only, right? So this is the incident ray, right? Where is the object distance now here? Object distance are always measured from pole. I am measuring like this, right? Am I measuring in the direction of incident ray or opposite direction of incident ray? Here I am measuring opposite to the direction of incident ray. Then the whatever the object distance what we get, that should be taken what we say here negative, right? That is the rule, right? Distance measured in the direction of incident ray is taken positive, whereas distance measured in the direction opposite to incident ray is taken negative, right? So what is the sign convention for object distance now here? Negative. If it is a 10 centimeter, u is equal to minus 10, right? Okay, let me check out here, right? Where is the object? Okay, here is the object. Okay, what is the object distance? It is the distance from the object from the mirror. Okay, from where? From actually from pole of the mirror. Distances are always measured from pole of the mirror. Okay, where is the pole? So this is the pole here. Where is incident ray? Incident ray always comes from the object. Okay, this is the direction of incident ray. Okay, object distance. From where I need to measure the object distance? I need to measure the object distance from the pole itself. Okay, let me take from the pole I am measuring the object distance, that is u here, right? Okay, come on, tell me now, u is positive or negative? Here also u is negative, object distance is negative. Why? Because the direction is opposite to that of incident ray, right? In both the cases object distance are negative, right? So like this we will be using. This is, do you understand? These are the object distances, right? Do remember, in optics, in mirrors, distances are always measured from pole. Okay, you need to remember this, right? Okay, for example, if I'm taking like this, we know that this is concave mirror and this is convex mirror. Where is center of curvature? Okay, what is center of curvature? Complete this. I need to complete this sphere. If I complete this sphere, I will be getting a center like this, imaginary sphere. If I am taking center like this, okay, let me remove this, right? So what is this now here? This is center of curvature. Okay, come on, tell me, what is the radius of curvature? Radius of curvature is the radius of sphere of which mirror is the part. So where is radius? So this is radius. So let me tell you, this is a radius of curvature. The question arises here, is radius of curvature positive or negative? Let me check it out. Okay, where is incident ray? Incident ray, where is the direction of incident ray? The direction of incident ray is in this direction, because object is in front of the mirror, right? This is the reflecting surface, means incident ray must be in this direction, right? Okay, come on, tell me, how to measure the distance of radius of curvature? Okay, we need to measure the radius of curvature from the pole, right? From the pole till center of curvature, that gives radius, that gives the radius of curvature. Come on, tell me. In concave mirror, what is the radius of curvature? Is it positive or negative? It is negative. Why? Because the direction is opposite to the direction of incident ray. So in concave mirror, radius of curvature is what we say here? Negative. Now, let me check it out about convex mirror. Come on, tell me, what about convex mirror? Imagine a sphere. Always we need to imagine a sphere. Where is the center? This is the center. Where is the radius of curvature? Radius of curvature is radius of sphere of which mirror is a part. Where is radius of curvature? This is radius of curvature. Now, come on, tell me, what is radius of curvature? What is the sign convention of radius of curvature? Is it positive or negative? Let me check it out. Where is the direction of incident ray? Of course, the direction of incident ray in this direction itself. It cannot be in this direction because it is not a silvered surface. Reflecting surface is this side, right? So this is the direction of incident ray. Come on, tell me now, how to measure radius of curvature? Radius of curvature is measured from the pole of the mirror. Okay, where is the pole? This is the pole. Okay, I need to measure it from the pole. Now come on, tell me, what is the sign for radius of curvature? Here the sign of radius of curvature is positive, right? So why it is positive? Because this direction is in the direction of incident ray. If it is in the direction of incident ray, radius of curvature is positive. If the direction of radius of curvature is in the opposite direction of incident ray, then we must take it as negative, right? So do understand this. Okay, these are the sign conventions. Okay, let me remove this again. Just it is an, for understanding's sake, let me take like this, right? Radius of curvature. Come on, tell me. Now, shall I ask you one question here? What is the sign convention for focal length? What is focal length? It is a distance between a principal focus and pole. Okay, where is principal focus? It is in between this, right? We have studied this. This is the principal focus. All the rays converge at a point. Okay, what is focal length? This is the focal length. Come on, tell me now. Is focal length positive or negative? Distances are always measured from pole. Okay, distances are measured from pole. Let me take what from this pole I am measuring focal length. Distance is like this. Where is the direction of incident ray? Incident ray direction is this itself, right? So because that is the reflecting surface, incident ray is in this direction. Now come on, tell me, focal length, is it positive or negative? Here the focal length is what we say here, negative, because the direction is opposite to that of what we say here, incident ray. So let me take, this is focal length. Now come on, tell me, where is focal length here? Okay, let me remove this. These ray, the parallel rays which fall on the convex mirror, they diverge and they appear to come from a point, and this point is called as principal focus. What is focal length? Distance between pole and principal focus. Distances are always measured from a pole. Okay, what is focal length? This is the focal length. And what is the direction here? Direction of focal length is like this. It is from, distance are always measured from the pole. Okay, where is the direction of incident ray? The direction of incident ray is this itself, because here is the reflecting surface. Now come on, tell me, is focal length positive or negative? So direction is in the same direction of the incident ray. Here the focal length is positive, right? Do you remember, the focal length is positive, it is in this direction, right? Okay, let me conclude like this. For a concave mirror, right, radius of curvature and focal length are negative. For convex mirror, radius of curvature and focal length are positive. Okay, do you understand? So these are the sign conventions what we use for the mirrors, right? Okay, let me move on to the third Cartesian sign convention, that is height measured upwards from principal axis is taken positive. Now let us check it out. What is the height of the object? Right? Can I take it as positive or negative? Okay, for example, if I'm taking, I told you, since this is a reflecting surface, we need to stand here, right? Now, who is the object now here? This is the object. Come on, tell me, what is the height of the object? Is it positive or negative? Remember, the height of the object, see here, height measured upwards from the principal axis. Height is always measured from the principal axis, right? From the principal axis means like this, right? This is the height measured. So this is the height now here, right? So if the height is measured upwards from the principal axis, then it is taken positive, and here the height is taken, what we say here, positive. If right? Object is in this. Okay, let me remove this. If the object is like this now here, right? If I am taking, if the object is like this in this direction, now come on, tell me what is the height of the object now here? Height of the object is negative, right? Because here, whereas the height measured downwards is taken negative. If I am taking, this is the height now here height is negative because the height is measured from the principal axis now here and it is downwards, right? So height measured upwards is taken positive, whereas height measured downwards is taken negative, right? So this is the height depends upon where actually the object is, right? Is it upwards or is it downwards, right? If the object is here, right, object must be in this direction. Object cannot be that side because there is no reflecting surface here. He has the reflecting surface here, object must be here. Here, if it is like this, the height is taken, what we say here, positive. If it is in the reverse, then the height is taken negative. Right? So these all are the sign conventions used for mirrors. Once again, let me summarize. All the distances are measured from pole. Right? If the direction of the distance measured, right, is in the direction of incident ray, then it is taken positive. If it is in the direction opposite to incident ray, then it is taken negative. Right, and height measured from principal axis upwards is taken positive, and if it is measured downwards now here, then it is taken negative. So these are the sign conventions to be used when we consider the mirror. Let us derive the relation between focal length and radius of curvature in case of mirror. That is the first derivation of this chapter. That is derivation of relation between F and R. Derivation of relation between focal length and radius of curvature. Okay, let me derive it. Now, let me consider a concave mirror. This is a concave mirror. You know, concave mirror is a mirror whose reflecting surface is inside the curve. So let me take like this, and here, where is the reflecting surface? Inside the curve. You can see your face from this side. So this kind of mirror is called as a concave mirror. Okay, let me start with the derivation. Consider a concave mirror. Okay, for this derivation, I am considering a concave mirror. Okay, this is a concave mirror, and where is the pole of the mirror? Midpoint of the mirror is called as pole, and we denote it by P. Let me write. What is P? P is pole of the mirror. Now, where is center of curvature? You know how to find the center of curvature. Let me imagine a sphere here. Okay, let me imagine a sphere, and the center of sphere is the center of curvature. Center of sphere of which mirror is a part. So that point is called as center of curvature. Okay, what is C? C is center of what we say here, curvature. Where C is the center of curvature. Let me remove this. Just imagine to get where actually the center of curvature is here, right? Okay, now C is center of curvature, and we know that this mirror is called as converging mirror. When parallel rays of light fall on the concave mirror, they converge at a point. So this mirror is called as converging mirror. Before I go with this, let me draw a line which passes through center of curvature and pole, and that line is called as a principal axis, main axis, right? So this line is called as principal axis. Now let me get where actually the focus is now here. Okay, let me take here. Let me write this point is called as focus. Why it is called focus? If parallel rays of light fall on the concave mirror, they converge at a point, and that point is called as a principal focus, and we denote it by capital letter F. Okay, let me write here. What is capital letter F? Capital letter F is principal focus, or simply we can write it as focus. Let me write. F is what we say here, principal, what we say here, focus. Right? Now, we are finding the relation between focal length and radius of curvature. What is radius of curvature? It is the radius of the sphere of which mirror is a part. So where is radius of curvature? This is the radius, right? This is center of the sphere, and this is pole, and this is the radius of curvature. Shall I write like this? So this is the radius of curvature. Let me write capital letter R, right? So where r is, what is r now here? It is a radius of curvature. Now where is focal length? Focal length is the distance between principal focus and pole. Where is focal length? So this is right. This distance is called as focal length. Okay, let me write. What is f now here? F is focal length. Okay, just these are the descriptions of the concave mirror which I have considered. Now let me take, if I am considering like this, where is the incident ray? Where does incident ray come from? From that side itself, because since it is a reflecting surface, object should be present that side, right? Okay, let me take this point. This is if a ray of light falls like this, and this is the incident ray. Let me take this as M, and let me take it as A, right? A ray of light falls on the mirror, and this ray is called as incident ray. Okay, what is incident ray here? MA. Let me write. MA is what we say here, incident, what we say, ray. Okay, come on, tell me. If I take incident ray, first you need to know where actually the light ray goes after reflection here. To know that, first you need to know where actually the normal is. Okay, where actually the normal? If I draw a tangent here, right, perpendicular, always passes from the center of curvature. We know the radius and the tangent are perpendicular to each other. Okay, need not to draw this. Understand that the line which passes from the center of curvature is nothing but the normal. So which is normal now here? CA is normal. Okay, let me write. CA is what we say here, normal. Now come on, tell me, if the ray of light falls like this, and this angle, what is this angle called? This angle is called as angle of incidence. Right, according to the law of reflection, angle of incidence must be equal to angle of reflection, right? Okay, this is angle of incidence, and angle of reflection, theta must be there, so it passes through like this. So this ray is called as reflected ray, right? And this angle, both the angles, if I am considering like this is theta, and this is also what we say here, theta. Right, so angle of incidence must be equal to angle of reflection, right? Okay, now which is reflected ray here? The reflected ray, let me write AN. AN is reflected ray, or AF is reflected ray. I can take like this. AN is what we say here, reflected ray. It is the reflected ray. Okay, CA is normal, AN is reflected ray. Come on, tell me next. Before I move with the next concept, just you need to understand, this ray is parallel to the principal axis. So this forms the letter, what we say here, Z. Right, then this angle must be equal to this angle. Why? Because those angles are alternate angles. Right, okay, what is this angle? Theta plus theta, that is 2 theta. And what should be this angle here? That angle also must be equal to what we say here, 2 theta. Okay, this angle MAC, and let me write that from law of reflection. From law of reflection, angle, which is that angle? Angle of incidence, MAC is equal to angle, what we say here, CAF, and that is equal to what we say here, theta. Right? If these are equal to theta, then from alternate angles, angle, which is that angle, AFP, that is equal to how much now here? Shall I write it as 2 theta, because these two angles are alternate angles. Now let us find what is the relation. Let us move on to the further things now here, right? Okay, come on, tell me, if this is 2 theta, come on, tell me, what is this angle mean? What is this angle? See here, this is also the Z letter which is formed. If this is theta, and this also must be equal to theta, again alternate angles, right? So if this is theta, this is theta. If this both is equal to 2 theta, this will be equal to 2 theta now here. Now let us consider the triangle now here, right? Okay, one thing what you need to understand, let me draw a construction here. Let me draw like this. Let me write it as AB, right? Since the mirror will be like this distance is too small, which can be neglected. BP is too small, which can be neglected. Since I want a right angle triangle, I am taking like this, right? I can take like this because this distance is too small. Now, let me take from triangle. Okay, let me take first triangle. What is that now here? CAB. Okay, this is the triangle, right angle triangle. What is that now here? From triangle CAB. Okay, from triangle CAB, I need this distance. So this is theta, right? Now, let me take like this. If this is theta, let me take tan now here. I cannot take sine and cos because we don't know this distance, right? So let me go with the tangent now here, right? Tan. Okay, come on, tell me from CAB, what is tan theta equal to? Okay, what is tan theta equal to? Tan theta, what is the meaning of that? Opposite side divided by adjacent side. Okay, what is opposite side of this triangle I am considering here? What is opposite side now here? AB. What is adjacent side? CB. Let me write AB divided by CB. Opposite side divided by adjacent side. Okay, which triangle did I take now here? CAB. This is the triangle which I am considering now here, right? Beside itself, let me take another one triangle. From triangle, okay, which triangle shall I take? This one, because this is focal length. FAB. This is the triangle which I am taking. From triangle FAB. Okay, from triangle FAB, again I will be taking tan because I don't know what is the hypotenuse here, right? I cannot take sine and cos. I need to take tan here, okay? Now, what is the tan 2 theta? Shall I take like this? Tan 2 theta is equal to, what is opposite side now here? AB. AB is the opposite side divided by, what is adjacent side? FB. Shall I take AB divided by FB now here? Now, let me move further now here. As this theta is small now here, right? Okay, let me take like this. As theta is small, right? What happens if theta is small? If theta is small, tan theta will be nearly equal to theta. Do you understand this, right? So, if theta is small, always tan theta will be equal to what we say here? Theta, and tan 2 theta will be nearly equal to 2 theta. Right? So, do you understand this? As theta is small, I can take like this. Do remember this. As theta is small, tan theta can be replaced by theta, tan 2 theta can be replaced by 2 theta. You know that, right? If theta is small, tan theta is nearly equal to theta, and tan 2 theta is equal to 2 theta itself. Okay, shall I replace it now here? Okay, here let me replace. Theta is equal to, what is theta equal to? AB divided by CB. Okay, here let me continue. 2 theta equal to, what is that now here? AB divided by FB. Now, in both the cases, one is common. What is that common now here? AB is common, right? In both the cases. Let me take what happens. What is AB equal to now here? Okay, shall I take like this? AB equal to theta into CB. Shall I take like this? And there again, let me take AB is equal to 2 theta into what we say here? FB, right? AB is equal to 2 theta into FB. Both are AB now. Shall I merge these two now here, right? Shall I take, let me mark. This is also AB, that is also AB. Shall I take like this? Theta into CB is equal to, what shall I take? 2 theta into what we say here? FB, right? So, since both are AB itself, shall I take like theta into CB is equal to 2 theta into FB, and in both the cases what will get cancelled here? Theta and theta will get cancelled. Come on, tell me what is CB? Okay, just remember here, what is CB? CB. Remember, this CB is equal to CP itself because this is too small. Since it is too small, I can consider CB is nothing but what we say here? Radius of curvature. Okay, do you understand? CP is actually the radius of curvature, but this distance is too small that it can be neglected. So, come on, tell me now what is CB? CB is nothing but radius of curvature. Shall I take like this? Radius of curvature R equal to, let me take 2. Come on, tell me what is FB now here? FB. This distance is nothing but what? Focal length. Why? Because this BP is too small to be neglected. So in case of FB, shall I say now here F, right? So R is equal to 2F. Then what happens? F equal to now here, right? By this, shall I say it like this? F is equal to, shall I take to that side, that is R divided by 2, right? So F is equal to R divided by 2. Focal length is always half of the radius of curvature, and this is the derivation here, right? What is the relation between focal length and radius of curvature? That is focal length equal to half of the radius of curvature. Do you remember? If I take C at a particular distance, F should be taken exactly at the middle, right? Principal focus will be exactly at the midway between the radius of curvature. Means this distance will be always equal to this distance, that is F is equal to R by 2 or R is equal to 2F. We can conclude here also, right? R is equal to 2F. That is the relation between focal length and radius of curvature. Do you remember? F is equal to R by 2, and this is the relation when we consider the mirror. Right. So the relation between focal length and radius of curvature, that is F is equal to R divided by 2. Do you remember? Let me conclude this session by giving an imagination. Okay, come on, tell me, which is this mirror? This is the reflecting surface. Reflecting surface is inside the curve. This is a concave mirror. Shall I imagine a sphere here? If I imagine a sphere, this center is what now here? Center of curvature. Where is focus? Exactly at the middle. Right, exactly at the middle. This is the middle. So this is what now here? Principal focus. That is how we need to understand, right? So we can imagine a sphere. If you imagine a sphere, center we will be getting, that is center of curvature. Exactly at the midway, we will be getting the principal focus. That is the relation between focal length and radius of curvature. Thank you.